Prêter le son. Alors, je vais remettre en mute pour l'instant. généralement. Ah, génial. Ouais, je commence. J'ai mis le micro là. Ah. Si j'attends, là, j'avais pas mis. Il faut que tu te mettes en mute. Ouais, faut que tu. Vas-y. Activé. Activé, tu m'entends? Bon? Ok. Je crois qu'on entend. Il y a marqué que Michael parle. Non. Non, c'est juste mon truc qui bug. C'est bien. Après, je vais essayer d'installer. Oui, au cas où. C'est encore en vacances. Comment ça, le 30 août? Je sais pas comment je vais faire mon micro. J'essaie de mettre le micro en même temps, mais c'est un peu galère. Là, vous m'entendez? Ouais. Un, deux, un, deux. Je peux dire un truc. Ça n'est pas trop là. Oui, je te vois. Oui. Ça, tu prends des notes? Tu prends des notes? Ah oui. Ok. Ah. Oui. Il me manque encore deux. Ah, je me suis fait trop bien. C'est un endroit. Oui, tu sors. Et les réponses, les autres réponses. Changer d'avis. Finalement, mais là, le modérateur, tu mutes tout le monde. Le modérateur, tu mutes les gens. Comme Mickaël a dit. Tu veux passer, on attend. Ah. Il manque Eric.
Hello Elsa, hello everyone.
Hello, Brice. Can you hear me and see me well?
Loud and clear.
Loud and clear, perfect. We are just waiting for Eric to arrive, and then we shall start. I guess it's kind of early for him, so I'm not I'm not surprised. Il doit être 8 heures du matin, je sais pas. 9 heures de moins. Ouais. Ici, tu penses? Ouais, 7 heures. Je voulais laisser au cas où quelqu'un a quelque chose. Après, on peut toujours avoir le message. Non, t'as raison, je vais peut-être enlever au cas où. Ok. Oui, c'est vrai que t'écoutes. Ah, je le sens. Une place silencieuse. Pendant 45 minutes. Le principe fait quoi comme ça? En fait, le micro pour les gens en ligne, c'est mon ordinateur. Oui. Ah, bah parfait. Hi, Eric.
Bonjour, bonsoir.
We have everyone.
Okay, let's see.
Okay, so I'll let the really next to the screen.
C'est pas moi qui défends. Hein. Will not defend. Already did. So I would like to welcome and thank you for attending this doctoral thesis defense of Miss Elsa Ducrot. It will be in English because we have several members of the jury who do not speak very well French. So I'm very glad that this defense could be organized at least partly in person. We still have some people which are attending remotely. So let me quickly first introduce the 6 members of the jury, starting with the external members who are attending remotely on the Zoom platform. We have Professor Eric Hegel from the University of Washington, Professor Didier Queloz from the University of Cambridge. We're very honored to have a Nobel Prize winner in this jury. Also very happy to have Professor Brice Olivier de Maury from the University of Bern. The supervisor of the thesis is Dr. Michael Gillon, Université de Liège. And in Liège, we also have Dr. Fran Pozuelos, who is the secretary of this jury and is attending remotely. And finally, myself, Denis Grodin, who will be the chairman of the jury. Before we start, I would like to quickly remind you how this defense is organized. Ideally, it should consist of 45 minutes of presentation by the candidate, which will be followed by 45 minutes of questions by the members of the jury. And after that, the jury will deliberate for about 30 minutes in a private room. Then we will return to this room and also return to the Zoom room after that, and we will announce the results of the deliberation. So now may I ask all the persons who are following the defense remotely to turn off their microphone and their camera. I think you can do that for them, so that I can leave the floor to Elsa Ducrot, who will present the results of her doctoral thesis entitled Search for Habitable Planets Eclipsing Ultra-Cool Stars.
Perfect. I will let you sit down and then I'll start. Dear President, dear member of the jury and members of the jury online, colleagues, friends, and family, I am very happy that you are all there to attend this defense, either in person or remotely. I feel quite lucky to have this hybrid defense. I'm not sure I could have shared this moment with that many people in a normal time. So thank you all for coming and all for attending. So in the next 45 minutes, I will tell you more about the work I've been carrying out during my PhD under the supervision of Michael, and it is entitled The Search for Habitable Planet Eclipsing Neutral Stars. So let's dive in. Okay, first, perfect. First, I'll start with this slide. This is a slide of content, just to explain how it will work. On each slide, you will have a little indication on the top left, telling you which part of the defense you are in. The defense will be in 5 parts. First of all, the context and objective of the thesis. Then my contribution to the Speculoos project. The parts 3 and 4 will be all my work on the TRAPPIST-1 system. I will explain what it is. And the fifth part will be the summary and perspective of this thesis. So I believe the best way to introduce the subject is by dissecting all the terms of the title. First, I will start with, of course, search for, I guess you understand, then habitable planets, and in this case, exoplanets. First, when we say habitable planets, we know only one habitable planet for now, and it is the Earth. If we look at what makes the Earth special, we identify that it is the only rocky planet in the solar system that has a biosphere, and that all the forms of life that are included in this biosphere, they share a common feature, which is liquid water. All the cells are made of liquid water. So in this thesis, when I talk about habitable planet, we are looking for planets that can have liquid water on their surface. This is the definition. And then for this second part, so exoplanet, it means planet orbiting other stars than the sun. So let me just show you this illustration by NASA, just to tell you that the first exoplanet around a sun-like star was announced, this discovery was announced in 1995, and Didier is well aware of this discovery because he was behind it. And in the last 3 decades, there have been thousands of exoplanets that have been confirmed, up to 4,000, and way more to just waiting to be confirmed. So in a way, we know that planets around other stars than the sun are not rare. Back on habitability and on habitable planets, to have liquid water on the surface, it's quite complicated. If you look at all the different factors that should be taken into account, you can look at this diagram from middle of 2018, where all the different components are gathered in 3 different groups, and you see that you have to take into account all the interaction with star, all the stellar effect, but also the planetary system dynamic, if you have multiple planets, for example, and also the planetary properties themselves, like the mass, the radius, and all the chemistry, things like you can have in the atmosphere. So it's quite complicated to really size what habitability is. And because of this, when we look for habitable planet, we're going to use kind of a proxy, which is the habitable zone. We're going to look for planet in the habitable zone, which is a region around a star in which an Earth-like planet can maintain liquid water on its surface. So in a way, we don't say that if a planet is in the habitable zone, it's going to be habitable, but it is more likely that we can find surface liquid water on this planet. So if you can want to represent what is the habitable zone, you see for a sun-like star, it will be the zone here in green. If you go too close to the star, it will be too hot and it will vaporize the water. And if you go too far, it will freeze out. So it's a little zone in between. And if you have a hotter and bright star, the zone is going to be further away. If you have a cooler and fainter star, it will be closer in. So this is for habitable exoplanets. Then the second term is eclipsing. And for this term, I have to go back to the way we detect exoplanets. In this case, eclipsing is kind of the synonym of transiting. And when we detect exoplanets, the most ideal and logical case would be to just take a picture of the planet and analyze its light, for example. This is called direct imaging. It is possible in certain cases. I really wanted to show you those images because they were published during my thesis, and I really love them. This is 2 different systems where behind the black circle here, you have the star that is hidden, that is turned off in a way. And you can see the planets. Here you have 4 distinct points. This is spanning 6 years. You can see the planet orbiting. And over there, you can see the planet going behind and then reappearing, and it is spanning 5 years. So when it works, it's quite wonderful. But for those planets, they are all really massive. They're all really far from the star. And it is quite complicated and for now impossible to apply this technique to temperate rocky planets, to habitable zone planets. So unfortunately, for now, at least for the next couple of years, we will have to use indirect methods. And I myself used one method called the transit method, which is quite intuitive and works as follows. So in certain geometrical configuration, you can have the orbital plane of the planet that is almost parallel to the line of sight of the observer. And in this case, you will have the planet that transits the star. So if you monitor the brightness of the star, you will see it's quite stable until the planet passes and there is a drop. And then again, when the planet is going to be behind, there's going to be a second small drop here because you hide the planet coming from the light coming from the planet. Sorry. So you have the transit and then the occultation. Way smaller the occultation. Using only one transit, you can do a lot of science. So a transit looks like this. So you do a drop of brightness with time. We have several observables, like for example, the transit depth, delta F, which is the relative drop of brightness. You have the different durations of the transit, the full duration and the duration, what we call partial duration, which is only the duration of the flat bottom part. Then you have the mid-transit time in the middle. And finally, the limb darkening, which is really this curvature here on the transit. Using those observable, you can derive several physical properties. Notably, using delta F, you can have the ratio of the radius of the planet to the radius of the star. From the duration, you can get the period of the planet. You can also get the scale parameter, where A is the semi-major axis, distance from the planet to the star. The impact parameter, which is the minimal sky projected distance between the radius of the planet, the center of the planet and the center of the star. And you can even get the stellar density. So only with one transit, you can already do kind of a lot of science. You can also do some characterization, and in two different ways, either through transition spectroscopy or emission spectroscopy. If you, in the case of emission, in both cases, you play on the fact that the star has a spectrum that emits in all wavelengths, and the light coming from the star, it can pass through the atmosphere of the planet when present, and each atmosphere has some different molecular species. They can absorb or scatter several wavelengths. So for example, here, if you have a H2O in the atmosphere, there's going to be some absorption in the infrared, whereas they will not be in the visible. So the apparent transit depth is going to vary with the wavelengths. This is called a transition spectra, where you monitor the transit depth versus the wavelengths over there, and you see that it can vary a bit. And if you compare the different models with molecules, you can recognize some atmospheric features. For example, here for WASP-39b, a giant big planet, you can recognize some feature corresponding to H2O over there. So this is for a big planet. We don't have such a good precision for temperature ones for the moment. And the second method is emission spectroscopy. This time when the planet is hidden behind the star, you can deduce which part of the spectrum corresponds to the planet and which part corresponds to the star. So you can isolate what is directly coming from the planet, which is a combination of its thermal emission and the reflection from the star of the light of the star. Again, you can identify some different atmospheric features and tell you about the composition, but you can also get, for example, the temperature profile of the atmosphere. And finally, now that I have explained habitable planet and eclipsing, I will tell you more about ultra-cool stars, what these terms mean. First, so what are ultra-cool stars? To explain this, I have to show you the Ersposten-Russell diagram, which is showing the different states of the evolution of the stars. Here on the y-axis, you have the absolute magnitude, which is kind of equivalent to the brightness, to the brightness, and over there you have the signal type, which is equivalent to temperature. In gray, you have the main sequence, which show you the zone where the stars are still fusing hydrogen in the core. And then you have different other evolution states, like from really evolved stars, like the giants, giants, or white dwarf. The stars that I'm going to focus on are the coolest and the dimmest, the really late M, what we call late M, and those are called ultra-cool stars. If you look at the spectra, they are quite different from the one of the sun. So in yellow, it would be the spectra of the sun, really black body shaped. For mid-M, it would be more the one in the red, shifted to the red. And for a late M star, like TRAPPIST-1, it would be even shifted to the infrared with many absorption lines. And then the big question is, why ultra-cool stars? And the answer is threefolded. First of all, because it's easier to detect the terrestrial planet around an ultra-cool star. This is due to the fact that the relative total brightness, delta F, is proportional to the radius ratio of the planet and the star. So if you have the same size for the planet, but you have a smaller radius of the star, you're going to have more signal. And this is detectable with ground-based facilities. The second answer is because it's more common in the solar neighborhood. So if you take the solar system and you look 10 parsecs away in all the stars around us, so on the y-axis is object within 10 parsec. And here is the mass, so high mass is over there, low mass over there. You see that you have way more of this red dwarf, which are those ultra-cool stars. And then the third answer is because, as I said, the habitable zone is going to be closer to the star. So you have a higher probability of transit for those planets around ultra-cool stars. There are more chances that transit happen. And also, you will have shorter periods, and so you will have more transit. And the more you accumulate transit, the more you can have better error bars and better precision. So there really is an opportunity over there. And this graph will summarize all of it. Like in blue, you have the probability of transit versus the different mass, high mass over there, like mass of the sun here and lower mass here. In red, you have the transit depth. And in black, the number of transits of orbit per year. If you want to maximize all those factors together, all those metrics, you have to eat in this green zone over there. And in this green zone, what we say is that if an Earth-sized planet was to be found around one of the habitable zone of one of these targets over there, it could become directly a prime target for characterization with the James Webb Space Telescope. So I will introduce quickly what is the James Webb Space Telescope. It is a giant telescope that is going to be sent to space at the end of the year. If you compare it to Hubble, which is more well-known, you can see how bigger it is. So the primary mirror is going to be 6.5 meter versus Hubble 2.4 meter. And it's going to be dedicated to the infrared and perfectly suited to look at those ultra-cool stars. So this zone is really the sweet spot of James Webb. If we compare in terms of capacities for James Webb for the transit transfusion spectroscopy, this is the relative transit depth, and this is the wavelength, and you have the spectra of the predictions for different types of stars. For example, in blue, it's going to be for an M3.5. You see that the amplitude of the signal is really small. For an M5.5 in orange, it's a bit better. You can hope to detect it. You know that the precision of James Webb is around 10 ppm. So you're on the edge. But if you eat for an ultra-cool star, an M8 like TRAPPIST-1, this is way better, and you can really hope to maybe detect some of those signals. So there is really an opportunity here to plan for James Webb, and this is why the Speculoos project was created, and it's going to look exactly at those targets. So the second part of my defense will be on the Speculoos project. First, I have to explain what Speculoos mean and also what TRAPPIST mean. So Speculoos is exactly the title of my PhD. It's the search for habitable planet eclipsing ultra-cool stars. And TRAPPIST, which was extensively really useful for Speculoos as the prototype survey of Speculoos was carried out on TRAPPIST. It means Transiting Planet and Planetesimal Small Telescopes. So both amazing acronyms, and you can see the Liège touch in each of them. And if I present to you the family of telescopes, because they are all really nice, you have the TRAPPIST South telescope, the oldest one. Then you have this twin in Morocco, in Ogaïmden. So this is for my family in Morocco. There is a telescope there. Then we have the 4 Speculoos South Observatory, the 4 telescopes in Chile, in Paranal. So Speculoos South Observatory, or SSO. You have the Speculoos North Observatory, SNO, with Artemis in the Canary Islands. And finally, the last one, Syntex in Mexico, which is the most recent one. So if you look at around the world, you have a bit of a Trapezosphere in Chile and in Morocco, Speculoos in La Palma and in Chile, and a bit of Poesy with Syntex in Mexico. So what happened is that every night during my PhD, or at least 1 week per month, I connected to the telescope to start the operation. This is just a screenshot of one of the webcams that look at the telescopes. We start with the observation, and the telescope goes directly by itself. It's a semi-robotic. It's going to go look at one neutral stars hidden somewhere over there. After we have all the data, so I was involved in data reduction, data analysis, data interpretation. I also even did some mission on site, so I was really lucky to be involved in all aspects. But the first year, a couple of questions that really made my work were that how do we know which star to observe? Which one are the ones that should be observed first? What is the global strategy of the project? And how do we schedule all this? So in the next couple of slides, I will tell you about the scheduling and strategy, which were all the work for my first year of PhD. I will just show you I will first talk about the target selection, then the ranking, then the observation strategy, the observing strategy, and finally the scheduling. So first, the target list, I have to say that the figures that I will show are coming from a study led by my colleague Daniel Sebastian, which I highly contributed to, in particular on the strategical aspect. So for the target list, first we have to set the target list for Speculoos. What is the target list of Speculoos? For this, we looked in the Gaia catalog. We looked 40 parsecs around us, and this is all the M and L stars. You can see we have a lot of M4 around us, but we selected only the coolest one. So the one in green are going to be the ones that are in the Speculoos catalog. This represents 1,600 targets, and then it was divided in 3 different programs. The first programs were approximately 300 targets. That's where the most interesting were for us, the one that had an SNR velocity superior to 4. What this means is that they have a signal-to-noise ratio that is achievable in transmission spectroscopy for an Earth-like planet, observed around 200 hours with James Webb, that is superior to 4. So this is really James Webb oriented. We want to prepare for the best target for James Webb. We want to catch planets around the best star. Then the second program is playing on a little overlap that we have with the TESS telescope that I forgot to mention before. TESS is going to observe the nearest star around us, the brightest star. It already has detected a lot of planets, and it can do some capacities for the LOMA stars, but it's going to be quite low significant signal. So the idea here is to play on this overlap to catch any low significant transit signal, and then try to confirm them with the Speculoos telescope that have better precision, just not the continuous covering that TESS has. And finally, the third program will be everything that is not covered by program 1 and 2. And this is really the statistical survey aspect to answer the question, how likely it is that there is a planet around a neutral star? Is it common or not? Then there is the ranking. So for the ranking, we want the best star to observe first. For this, we use this SNR symmetric again. This is the test spectral type, so equivalent of temperature is the coolest one, the hottest one. Here you have all the stars 40 parsecs away, around us. And if you want only the Speculoos target list, this is after the black line on the right. And all the ones that are in the program 1 are above the red line. You can see TRAPPIST-1 that is indicated. I will explain later what is TRAPPIST-1. And the idea here would be to aim for the highly ranked target, the one that is on the top over there. And if we find a planet around one of these stars, it would be directly an amazing target for James Webb. But of course, we have to check that this target is observable from the sites that we choose, like is it observable from Chile or from Mexico or from the Canary Islands? When it is observable, can we coordinate between different sites? So all of this is taken into account in the ranking. And then there is a strategy. So how do we want to observe the target? Do we want to observe one target for 20 minutes, then the second one, then the third one, and we come back to the first one? Or so this is a splitted strategy? Or do we want to observe one target as long as possible, the full night, for example? This is a continuous strategy, so we have to choose between the two. And to decide which one is better, I use what I call the effective phase coverage, and I will explain you what I mean with this graph. Here, this is, for example, for a target that's called SP0643, so funny name. It's one of the speculoos targets. It was observed for 34 hours. And what I looked is how much each period was covered in terms of phase coverage. So for example, for 4.7 days, I took all the observation that we had. So all the arc circle here in blue are night of observations. You faithful it on a 4.7 days period, and you see how much you cover the phase. So you see here it's almost filled, but you have some gaps in the circle. So the coverage is not 100%, it's 80% in this case. And you do this for each period, you calculate this coverage. And then to get the effective coverage, you just integrate around on the period range. So I use this effective coverage with simulation. This is real data, but I did simulation of different scenarios, every time with different period ranges, and I choose which one was giving me the best effective coverage. And it was the continuous observation one. So for speculoos, we use continuous observation strategy. We try to observe one target all night long. If not possible, we observe two targets in the night, but we don't split in between several targets. And the next question was to understand how many hours do we have to accumulate on a target for it to say, okay, we are done on this target, we can go to another one. To answer this question, you have to come back to the title of the thesis, which is Search for Habitable Planets. So we want to cover the habitable zone, at least for a significant coverage. So here is the evolution of the effective coverage versus the number of hours observed. All the points are real observation, real points of speculoos targets that have been observed with the telescopes. The color bar aimed for the localization of the habitable zone for those stars. Some of the stars are cooler or hotter, and so the habitable zone is going to be further or closer to the star. In this case, if you take the habitable zone, if you are in the middle, this corresponds to a period, and this is this period. We want to cover all the period of the mid-habitable zone of each star. All the lines are simulations, so simulations of the strategy, but not real data. So you see the simulations are quite consistent with what we observe, so that's already a good exercise. And then we can look at, in general, the most targets of the mid-habitable zone period around 8. If we want to cover at least 80% of this period, we have to go at least to 200 hours. And if we go above, we're not going to increase much. If we want to get the last 10%, you have to increase a lot the number of hours, which is really time consuming. And of course, your survey is going to last so many more years. So the best compromise is to aim for 200 hours. So you can cover at least 80%, and for all targets, even the one that have an habitable zone period at 12 days. To put the strategy into, to make the strategy work and send all the plans and all the indications to the telescopes, I developed this code that I call SPOC, as like so many codes in astronomy, but it means Speculoos Observatory Schedule Maker. And the idea is accessible and open access on GitHub. It is all written in Python. There is kind of a user-friendly app to ease your life and to make all the scheduling. And it allows you to schedule anything in the core program of Speculoos or external program with test follow-up or any special object. Here I just show what the documentation looked like, just to show that in just a few lines of Python, you can do pretty much every command. So just showing what the scheduling looked like at the present time. This is the magnitude, so brightness in G-band. G-band is well adapted, well suited for James Webb, versus this SNR diversity metric. And number of hours survey is a color bar. And you see that we are slowly increasing the number of hours on the highly ranked one and slowly getting to fainter targets. So the strategy is in agreement with the result, of course. And then you have this TRAPPIST-1 again, TRAPPIST-1 star that is indicated here with a dotted line. And it is the third time that I mentioned this system, so I think it's time that I just go to the third part and I tell you more about TRAPPIST-1 and what it is and the different aspects. First, I will talk about the Spitzer campaign. So first, okay, just to tell you what is TRAPPIST-1. TRAPPIST-1 is a neutral cool star. It's an M8, and it's way a bit older than the Sun. It's way smaller and way less massive, only 12% the radius of the Sun and 9% the mass of the Sun. It's half its temperature, so way cooler. And it is orbited by 7 Earth-sized planets, which have really short period, like 1.5 to 18 days. Way more compact than our own solar system. If you take a look at the radii, masses, and radiation of those planets that they receive, it's kind of similar to what the terrestrial planets in the solar system have. So this is really interesting. And if we look a bit closer, we can see that we have 3 planets within the habitable zone. So that's quite exciting. Again, you can see how compact the system is because it's really enlarged 25. So all the system can fall within the orbit of Mercury. The star is way smaller, as you can see on the illustration. And of course, the planet endure really different environment in terms of habitability because they are so much closer to the star and also so much closer to each other. So this is about the basic properties. And I said Spitzer campaign, it's time that I mentioned what Spitzer is. So Spitzer is a space telescope that dedicated a full exploration program to TRAPPIST-1. Actually, the largest program ever performed on one single target for exoplanetology. And it will accumulate more than 1,000 hours from 2016 to 2018, including 20 days of continuous observation. So this is a short animation made by NASA about those 20 days of accumulation of data where you can see the light curve being drawn as the planet transit the star. So the different transit of different size because you have different planets. And I was extremely lucky because in the second part of my PhD, I was given the chance to analyze this full data set, full 1,000 of hours of data. This is just a snapshot of what the light curve look like, all the different transits with different size because you have different planets. So we have many transits to analyze. You also have some flares. I will explain what they are. And we also aim for some occultations, and I will tell you what we found. So first, about the transits, this is we observed in 2 channels at 3.6 and 4.5 microns. This is a phase folded transit for the 2 channels, and there are offsets just for clarity, so you can see. So for the deeper the transit, the larger the planet, and of course, if the direction is larger, it's because the planet is further away to the star. From this extensive analysis, I was able to refine the precision of some physical parameters. So for example, the precision of only a few % on the planet's radii and the equilibrium temperature, a precision of 1% on the semi-major axis, and less than 10% on the stellar density. So only using transit, which I find quite exciting. Then what I tried is using the 2 points in Spitzer, just to put them on a transparent spectra and see if I can say anything, even if I know that Spitzer is doing broadband photometry, which means that you have a big error bar in X, like this. But we had so many transits that the precision in Y here was getting really good. So I wanted to see if we can say something. I compared with other existing data, all the points in purple. You have a point from K2, a space telescope again. You have Speculoos in Liverpool that I've observed as well. You have the Hubble Space Telescope with the pale pink and some other facilities in the infrared. You have the VLT, very large telescope over there. And you have the Spitzer point. But as you can see, if you overplot, like what I did, some atmospherical model, it's quite impossible to say anything because the error bar is still too big compared to the amplitude of the features. So this little jump over there, it's a signature of CO2. And I wanted to see if we can start to have a hint of maybe the presence of CO2 in the atmosphere of TRAPPIST-1b, but the data is not good enough yet, maybe with James Webb. But I also tried to combine the spectra of B plus C, etc. to D to even decrease a bit more the error bars and see if I can find maybe a common behavior, like all the planets have an atmosphere rich in CO2 or something like this. If you compare to some models, this is an Earth-like model. And then you have a Venus-like model. And finally, a Titan-like model. So again, we are quite limited by the data. But if just for fun, we try to see which one fits the data the most, you can say that the Titan-like atmosphere is less likely. This is due to the fact that you have a CH4 band over there in methane, a methane band that you don't seem to observe. So the first thing you can say is that it is less likely that all the Travis-Stone planets are CH4 dominated, but this is extremely limited by the precision of the measurements for now. And Spitzer was not dedicated to this. It was just a kind of a bonus conclusion. And of course, we will have to wait for James Webb to cover all of this range and do really spectroscopic observations. So maybe confirm this hypothesis kind of conclusion, or maybe not. So we'll see. We also looked at the occultations. So here, this is from the paper I published. You have the faithful occultation for 28 occultation of B, and this is for 9 of C. So you see the errors, the points are really spread, and the curve is really flat. So we did not detect the occultations. We did not see them. I recall that occultation is when the planet is behind the star. The only thing I could say is that I know which precision I reached with Spitzer. I managed to reach a precision such that if the transit depth of B was this large, 180 ppm, I should have detected it. And if C was this large, I should have detected it. If I don't, it means that the brightness temperature of the planet cannot be higher than this for B, and cannot be higher than this for C. So this is the first constraint. It seems to be just an upper constraint, but actually, it is the first time that we get such constraint on a temperate terrestrial planet. So it is a still exciting result. And again, James Webb will have an instrument that can do way better for the observation of occultations. So hopefully next year or the year after, we'll have a conclusive detection. Another thing that I did with all those transits in Spitzer is to get all the timings, to do a transit timing monitoring and study the variations. So when you have a multiple planet system, all the planets gravitationally interact with each other. And so the orbits are not really Keplerian anymore. They can be like decelerate and accelerate on their orbits, different planets. So the transit can happen a bit early or a bit late or on time. And this is cyclic. If you look at the different evolution of CTD, so transit timing variations over time, for example, for all planets, for B, it's more like 2-3 minutes. But for the outer planet, like F, H, or G, it can be up to 20 minutes, minus 30, then 20 minutes again. So it's varying a lot. You can really monitor them. And then after, when I got all those timing, I sent them to my colleague, Eric Agol, who is in this jury today. And Eric led a big analysis of all those TTVs. This is the best fit model. So he used a dynamical model to fit the timings in order to derive the masses of the planet with great precision, and also the orbit, and even, like, for example, the eccentricity, etc. So here you see the fit in green and in blue for different planets, the 7 planets. The points, the timing I sent him are here in red and orange. The fit is really good, and he was able, using this, only transit timing, using only TTVs, he was able to refine the masses of the planet to a precision of 3 to 5%, which is extraordinary, as it was never done for such Earth-sized temperate planets. Then if we look at the mass radius relation, we have the radius over there, the mass over here, and the equilibrium temperature is shown with the color over there. And the little shapes here are the joint posterior for the different planets. This can tell you about the density of the planet and the interior composition. So here in the dot line of the composition of the Earth. This was before. This was the first analysis led by Simon Green in 2018. And we had this information on the mass radius relation. And now, comparing to what Eric got using all the Spitzer timings and a couple of way more transits, you can see really that the errors shrink totally. So we really start to understand and to feel the real masses and real composition of the planets. So here you can pass a line through all the planets. They seem to be on a single composition line, and they seem to be all a bit less dense than Earth. So this is really exciting because it was so much better using all those timings. And it is the first time that we get such good precision on terrestrial planet. I think these are the terrestrial planets that we know the most after the terrestrial ones in our own solar systems. And because of this, because this is quite kept thrilling. There are some ongoing analysis, and I'm leading the analysis of all those transits of Stephilos and Liverpool to do many things, analysis of system parameters, etc. But in particular, to be sure that the prediction of the model are still correct. So the model is here in dark. The points used in Eric's study are in yellow, and all the new ones are from the transit that I'm currently analysis. So I'm accumulating many transits. This is for the 3 outer planets, the outest one. So that's why you have less. For example, the period of H is 18 days, so you have less transit, of course. And what I want to find is maybe a few outliers that can tell me if there is something that we might have missed in the model. So there seems to be an outlier over there, and it's not really confirmed. Maybe it's a single event. So we must continue monitoring, and maybe this will give us a hint of an 8th planet, for example, that is hidden that we didn't see yet, but that maybe the dynamic can tell more about. Then I mentioned some flares. And here I will tell you about the flares and periodic chemistry. So to simplify, I just uploaded this drawing of a chain. This is really simplistic, but there was some experiment carried out by Riemer 2018, saying that if you have some far UV on a kind of a periodic soup, you can create what we call a pyrimidine ribonucleotide, which is this molecule here, which is a building block of RNA. And RNA, in some scenarios of astrobiology of the apparition of life, there is the RNA world that maybe led to probiotic chemistry and to the apparition of life. So this is a really raw and big picture, but if you have UV emission, can allow you to go to the emergence of life. So this study, they defined the abiogenesis zone, which is a zone where you receive enough UV flux to trigger this kind of chain reaction. And if you look here, you see the Earth here in red, that lies within the habitable zone and also within this abiogenesis zone. So great, like emergence of life can happen on Earth. So we knew about it, but it's still nice to see. And if we go to other like cooler temperature here, in shorter periods, you can find the TRAPPIST-1 E, F, and G. So the 3 habitable planets of TRAPPIST-1. And you see that they are not receiving enough UV flux. Indeed, if we look at the spectra of TRAPPIST-1, it's way different than the sun. And in the UV, in the far UV that we want, it's really calm. So we don't have enough of this UV light. And this is why maybe flares, which are a sudden outburst of brightness that can have a stronger UV component, maybe those flares can change a bit the shape over there and bring those planets in the abiogenesis zone. So this is what I looked at. I looked at the flare frequency distribution. This is the flare frequency, the cumulative flare frequency versus the flare energy. My work is in red compared with other work that I used where I analyze the K2 flares. And we have those slopes. If you want your planet to be in the abiogenesis zone, you want those slopes to cross one of the zones. So in the green here is the abiogenesis zone of B, and in blue it's the abiogenesis zone of E. And for V, F, H, etc., it's going to be even further away. What we see is that none of the planets seems to receive enough UV flux to build up the probiotic inventory. But if you look at empirical study, it seems like a younger TRAPPIST-1 might have been way more active, in particular in the pre-min sequence phase. So maybe a younger TRAPPIST-1 could have crossed this zone. And as the abiogenesis zone is not like the habitable zone, you don't need to remain in it. You just need to kind of trigger it like like a lighter. We can expect, or maybe it's of course all hypothetical, but maybe planet E, for example, has received enough UV flux in its history to drive this emergence of life and then prosper. But this is just a scenario. So talking about stellar magnetic activity, I'm going to transition to my last part, which is the stellar contamination, back more on the observations. And first, I will tell you what is stellar contamination. To explain this, I must say that the star, this is the big picture of the sun, real picture of the sun. The star is not really homogeneous. You have most of it that is called a quiescent photosphere, but you also have some features like spots or faculae. Spots are black, cool features, and faculae are brighter and hot features. And those things, they can really impact your observation and your analysis, either by when they are on the transit course, so where the planet passes, or outside the transit code. If we look what is the impact inside the transit code, you can see that when your planet passes, if it passes in front of a black spot, it can create a bump like this. And if it's going to be a hot spot, it will create a dip. So it modifies the shape of your transit. And if you do your fit after this, without knowing about those shapes, maybe your best fit is going to pass through over there, and maybe you will have really different transit parameters, which will imply different physical parameters. So it will be mistaken. So you have to take those into account, and they can be can lead to some mistakes. Then you have also the impact of those features when they are outside the transit code, and this is more like a spectral contamination. In your transition spectra, what's going to happen is that you're going to have a spectral difference between the transit code and the rest of the star. It's not exactly the same spectra, and this will create spectrum. This will create different features that can mimic some atmospheric features. So maybe we can mistake some features saying, oh, this is I don't know, H2O, but actually it's stellar contamination. So there were some predictions in 2018 by this work led by Ben Rakam on TRAPPIST-1. And the simulation using this three-component model, so quiescent photosphere, faculae, and spot, was quite negative because they say that it can be up to 25% the relative depth change in terms of contamination. So if you look at this transit depth change versus wavelengths, you can really hide some of the features that you will be looking for, like O2 or H2O. So we have to look into it and see if the predictions are real. So during the first year of my PhD, I was in the first year, yes, I used observations to the rescue in a way that I analyzed a lot of transits over there. So except the ones in the UK AAT, those 4 ones that were analyzed by my colleague Artem Yordanov, the rest, I reanalyzed all of them in very different bands in order to see if I can agree with the predictions of those models. What I see here, so there was this model by Zhang et al. 2018, based on the one by Rakam et al. 2018. In the version 1, they say, in black is the model, they say that they expect a dramatic decrease of the transit depth in the visible, so in this zone, which was quite puzzling and really bad for interpretation. But I looked with the observation I had, and when I overplot those, I have a really strong discrepancy. So my points are in red, and the points that they predict are in the dark bands, because it's integrated on a broad range. So we see a strong discrepancy, and the model was totally rolled out. So this was a strong prediction because they say 30% of cool spot and 60% of hot faculae, so almost a two-component photosphere. But after my analysis were published, it was a revision of the model, so the V2 this time, where they managed to fit the 2 new points. So the scale is really not the same. The predictions are really less dramatic. This time the model fits the 2 points. But afterwards, I was able to add 2 new points thanks to Spitzer at 3.6 and 4.5. And again, this 3.6 points do not seem to fit the data, to fit the model at all. And furthermore, it was shown that those 2 models, V1 and V2, they don't agree. Like if you take the magnitude that you should have with this prediction, they do not match what we observed at TRAPPIST-1. So both of them were kind of rolled out. And now we have really different models for TRAPPIST-1. So as I said, like since then, there have been many new approaches, and the effect of stellar contamination has really become something really important, because there was the creation of this study analysis group by NASA, really dedicated to the study of this effect. And people are taking this seriously because there is some transmission spectroscopy to be done with James Webb, and we don't want it to pollute the interpretation. So now it's time that I go to my summary and my perspective to conclude this defense. The first part will be on speculoos. Just to say, I already said it, but I repeat that I was really lucky to be in all the aspects of the project. I've done kind of all the different steps. My main contribution was on the strategy and scheduling. It is kind of my legacy to the project. And I hope the code I developed will be used for the many years to come. I also took part in every discovery made by speculoos, thanks to the scheduling or to the data analysis. And this include many different objects, like the study of complex rotators, discovery of new planets, and even discovery of really rare objects. So we all hope for new planets around the so-called stars, other than TRAPPIST-1. And I really think there is a great hope with this synergy test Speculoos. So I'm looking forward to Speculoos 2, as many of the consortium. And then for TRAPPIST-1 and James Webb, so I didn't have time to mention it, but there are several simulations on the system that agree that we should detect signature of CO2, at least CO2, in fewer than 10 transits for all the 7 planets. So this is going to be quite fast and quite cool. We can also expect to have the dayside emission of the inner planet, TRAPPIST-1b. And this is something that's going to be done with the MIRI instrument. And I'm going to be taking part of it because I will join the MIRI instrument team at the CIA next year. I don't want to say CIA because I'm not an FBI. So yeah, I will be involved in this part. And then in terms of TTV, I wanted to show this order of magnitude because for me it's quite crazy that we can precisely have the timing of a transit with a precision of 1 second per transit. So we can really predict the transit with a precision of 1 second. For me, it's better than as good as the human brain, like when you time someone, so it's really good. And so because of all those amazing predictions, you will have the TRAPPIST-1 James Webb Community Initiative that has been created by Michael in 2020, that involves hundreds of scientists and really aim to unveil the nature of the planet. Just to say that the system is already going to be observed by 4 real-time observation and 3 guest observer program. This represents already 200 hours. So before the telescope is even launched, there's already 200 hours to be accumulated on the system. So many bright days to come. And I will finish on this positive note. And thank you for your attention.
Just activated my microphone. Can you hear me? I'm talking to the jury members. Yes. Okay. It's
Yes.
time that we start with the questions, and we have approximately 5 to 10 minutes per jury member. So we will start with Eric Egel. So go ahead, fire first.
Great talk, Elsa, and wonderful presentation.
My sound on.
Can you hear me? Is my sound coming through clear?
Yeah, I can hear you well.
Okay, yeah, great.
Can I see you?
I turned on my video now, so
yeah, I can see you.
Showing up on your screen. Okay, wonderful talk. Yeah, that's great work. And really looking forward to things coming that you talked about with James Webb, of course. Let's hope the launch goes well. Yeah, so let's see. One quick question I had. So you said continuous coverage was the best strategy with Speculoos, and can you remind me, are you observing several stars and iterating between them, or just continuously observing without any gaps each star?
So the thing is, maybe. Okay, sorry. So the thing is, of course, we have the day-night shift, so we cannot really be continuous 100%. And some of the targets, depending on the site you're in, sometimes you cannot do a full night because they don't go high enough in elevation. So you do the most you can at the highest point of the visibility. So my code is going to look at the visibility over the year for all the targets, and it's going to pick like the best months. So for example, like the best month is going to be in March. So in March, it's going to say the target is way highly ranked in terms of observability. And if possible, we're going to put it as much as possible. But for example, if the night is 8 hours and new block is 6 hours, you don't want to have 6 hours and then a small block of 2. So in general, if I don't have a full night, I'm going to split it in two with 2 targets. So I can have 2 equal lengths for the blocks. So I don't have like short little things in each night. I don't know if it's answered your question.
Yeah, and in particular, I'm wondering if you're going between several stars at once, or you continuously stare.
Because we have the different telescopes, so the field is quite narrow. So for one telescope, we go on one target.
Okay.
Sometimes we're quite lucky. We can have two specular targets in the same field, but this is pretty rare.
Okay.
And each telescope is doing one target.
Okay. Yeah, that makes sense. I thought for some reason I thought that TRAPPIST-1 actually was nodding between different targets so that you get continuous coverage, but with the gaps as you go between targets. But I think I'm confusing it with the M-Earth survey, which I think maybe has that strategy.
We have a different strategy indeed.
Yeah. So let's see. As far as the this scheduling and strategy, of course, if you have really bright stars with speculoos, you'll get much better signal to noise. And so is I guess in your ranking, of course, you also want the bright stars for James Webb, but in the targets for which you're doing the bulk of the survey, which look like most of the stars of the 1600 or so, those are going to primarily be faint stars. So does your for the bigger survey, does the sensitivity to Earth-sized planets really drop significantly because a lot of the stars are going to be fainter? So
I didn't have time to. Sorry, it's on this graph over there. It's charging. Can you see the graph?
Yes.
Yeah, on the ranking. So you have the color bar here, which is the SNR speculoos, what we call, and this is used for the program 3 to rank the program 3 targets. This SNR corresponds to, it's not talking about transmission spectroscopy here. It's just like the SNR you would get if you have one transit of an Earth-sized planet around the targets. So of course, you're right, it's better when you have a small star, but also it depends a bit if it's bright or not. So you don't necessarily have all the L8s that have the highest SNR in terms of James Webb. You need a cool star, a small star, but it's quite bright. So it's a compromise between the two. And you can see the color code on these figures if you want to see how the program 3 targets are ranked.
Great, cool. The other thing I wanted to ask was relating to the last or second, I guess the last part of your talk on the contamination. So I know in our conversations that you were discounting the HST depth as maybe it's harder to calibrate because it's in a low Earth orbit, and so you have gaps in each of the transits. And I'm curious if you have a sense for how much of an offset you might have due to the uncertainties in the absolute depth of the HST, because it seems to be the other 4 data points in the optical and with Spitzer, given the larger uncertainties in the optical, smaller uncertainties in the Spitzer, it kind of looks like that dashed curve that you have drawn there.
Yeah, so I guess
consistent with those, but HST is the outlier.
Yes, the best figure to talk about this is more on the transmission spectra. Here you see this is for B, and this is HST, but offset. So indeed, I applied an offset here to put them more consistently with the weighted mean. So of course it is weighted with different points. And I don't remember the exact value that I had to put. I don't remember. I think it was. I applied the same to all planets. So when I used the combined spectra over there, I applied the same to all planets. I don't remember the exact amount, and I'm kind of confused with those HST points. The fact that I have to put an offset is kind of puzzling to me, and that's why I don't really try to base my conclusion on HST for now, because the fact that only playing with the relative and not the absolute depth might be a mistake. I'm not really sure that we should be doing this. So that's why I don't really use HST in my interpretation. It's true.
Yeah. Well, hopefully James Webb will solve all this.
Yeah, that's what I hope to.
Fingers. Anyways, that's all the questions I have for the moment, but I'm happy to move on to the next question. Wonderful talk.
Thank you very much.
Thank you very much. Now, Didier Queloz.
Yeah, thank you, Elsa.
I can see you. I can see you. Thank you.
So I know quite well the work of Elsa because she has been spending a significant amount of time in Cambridge with us, And I must say that was always a pleasure having Elsa around. So essentially, I'm very impressed by the works, a bit like a fireworks of many different aspects and topics. And I think I was very impressed by how much she could just survey all she has been doing in 45 minutes. That was quite a challenge here. So well done. So that was really good.
I think it's
So-
fast.
Well, I think you're speaking fast. It helps. So I don't want to go into too much detail on some aspect, but I would like to come back to a couple of general elements that you mentioned. So maybe 3 elements here. The first one you mentioned about, you talk about habitable zone, mentioning this is defined by liquid water on surface. You clearly explain how we get a good understanding of the nature of the TRAPPIST-1 system. But I mean, what is your understanding of how, let's call it accurate in that case, we should be on the size and the mass to really say something significant about the surface of this planet? Can we really say something? Can we say it's rocky? Can we say what kind of rocks? How far are you sure, even with the amazing, precision we have right now and living to an accuracy for the density, do we really understand these planets?
So for this, I'm going to use this is an additional slide, pretty much similar to the one I showed. Just it's coming from Eric's paper. Again, I forgot to put the reference, but of course it's Aguilera 2021. And this is just comparing the mass radius ratio relationship, with different interior compositions. So just to answer your question, of course, this was there are some scenarios that have been hypothesized, either because they are a bit less dense than the Earth, than the terrestrial one that we know. We want to explain why, and there are several scenarios, either because maybe they will have a core-free planet, which is kind of an exotic scenario, but I kind of like it because it fits really well with data. There is also if you have maybe a highly, maybe something with an Earth-like core, but more surface water on the content. So for example, like here you have different types of percentage of water that can maybe fit the data. But of course, it is kind of a degenerate problem because you can fit several scenarios to this. There is no clear answer. I agree with you. And can we really get on the surface? I'm not really sure when, but I guess, so I think it's explained in Eric's paper. Kind of the limiting factor here is also the knowledge on the stellar parameters, even more than the precision in TTVs. So maybe the big click is going to come from this aspect. And this could really even shrink even more the error bars of this joint posterior and maybe start to really differentiate between different scenarios. But it's true that right now, the problem is still degenerated. So it's hard to say the real composition of the planets 100%. I agree.
Could you, because you show this diagram, that's a quite fascinating diagram. Could you maybe explain a little bit what is this FA over mg? I mean, because you do have the red, let's take only these 2 lines. I think the red and the black, and they all fitting kind of all the objects. They are different from the Earth one. So, I mean, how can we, I mean, what do we do with that? I mean, because if you compare, strictly speaking, with the Earth, they are different. They are not the same.
No, it's true that we know that the planets are not expected to be Earth-like composition, that's for sure. But so the red one, the one that fits really well, it's the core-free scenario. I think it was, in the paper, it was discussed by Caroline Dorn. There is another paper discussing this. I don't remember the exact reference. But the idea is to imagine that you don't really have a core. It's like highly oxidized. And so you kind of have all the planets that is high oxidized iron. So this is quite exotic and it could fit, but I don't know what it would imply, because if you don't have a core, you don't have the same magnetic activity. And so I'm not really sure how the planets are going to be protected from all the stellar winds and stuff like this. So this is, of course, to take into account. And then the second one, the black line, over there, it's really using an Earth-like core, but adding more water content to try to be less dense and to fit the posteriors. But here, because of all the 3 inner planets, for example, they're going to have be highly radiated, And so the water is going to turn to steam. So you can even have it's going to be a bit different. Like that's why you have model like water or steam, depending on the different lines.
Okay, so let's go for the water then. So we have Venus, which is a perfect planet to find life according to the criteria you mentioned, but it doesn't work. So I mean, do we have water in Venus? I mean,
but Venus is not in the habitable zone.
Venus is not in the habitable zone.
Yeah.
According to which criteria?
Depending on the boundary you use, but like on the conservative one, like if you are not really optimistic, it's not located in habitable zone, like it's in greenhouse, like a runaway greenhouse. So.
Okay, so let me just maybe go to another aspect related to that. And you clearly explained two techniques to get the spectroscopy of this planet, to get some atmospheric content of this planet, the transit spectroscopy and the emission spectroscopy.
Yeah.
Okay, keeping in mind this kind of problem we have to understand the surface of this planet, what do you think is the best to do? Atmospheric spectroscopy or emission spectroscopy on that planet?
So I'm a bit biased because I'm going to be joining Miri's team. But I will say,
I'm just asking you whether you could do both, or you can do only one of them. Not talking what you will be doing. I know you corner into a, but do you have some ideas?
I would say that emission spectroscopy seems to be less impacted by some contamination. In particular, stellar contamination that I mentioned in the last part is going to impact transmission spectroscopy, but not emission spectroscopy. So if you want to get over this issue, you can use emission.
Okay. But let's imagine there is no contamination. So the contamination is being solved. So imagine you don't have no contaminations. I mean, what is the best? What would you learn for each of them, or what you would not learn, or how far do you depend on the nature of the surface to understand what you're going to observe?
So in the emission case, as you get the direct light from the planet, you can sound, or you can really probe different layers also of the atmosphere. If you compare to transmission spectroscopy, you don't probe the same aspects, the same parts. So in a way, I would say if you want to analyze the direct light of the planet, you will have more information in emission. If you have in different wavelengths, you can have either the thermal emission or the reflected light, which can tell you about the albedo or can tell you about like the temperature of the planet. So I would say it's a bit more complete. And if I had to choose, I would go for it.
Do we have reflected light on TRAPPIST?
But we don't really have emission for now. So I guess there might be a component, but was never identified. Yeah.
Do you think it's a significant component? Oh.
I have no idea. Maybe the albedo of the planet is really strong, and I have no idea how the surface of the planet could look like. Okay,
let's imagine there is no atmosphere. So what would you do?
So it could be like if it's a bare rock. In this case, you will have only you will see it with the phase curve. You will have a strong reflection.
And if it is just bare rocks, what would you see in the transmission spectroscopy?
You will see no features at all. Like it would be pretty like it would be the same at all wavelengths.
Okay, there's no change. Okay, great. So I have a last question, which is a maybe a tricky question here. I think you did this wonderful program, Spoke, and it's intensively used and it's very efficiently used. It's helped us to observe all these many objects. But frankly, we're failing on that program right now because essentially without a very sophisticated strategy, TRAPPIST-1 pop on in the data with only one telescope. And then we have 6 telescopes and operating since more than 1 year, and we found none. So are we making some mistakes in the strategy, or is it something wrong we're doing?
So this is a totally good question, and I hope it's not coming from Spock. But so either the likelihood of planets around a ultra-cold star has been a bit overestimated, which is possible, or also maybe indeed we don't look right, or we haven't been so lucky. But the thing is, also there is a big intensive effort to do on the analysis of the data that I think we are trying to do now, because we have accumulated so many hours on all of those targets, and some of them, like the activity of those targets, is a bit more tricky than what we thought. So TRAPPIST-1 is exceptionally calm if we compare to all the stars we have in the catalog. Every night looking at the light curve, some of them are quite chaotic, even if we try to adapt the performance of the telescopes. So I guess there is a lot of, I would say, pre-processing to do before you really hint for the transit signal, or at least in simultaneous, you have to really correct the stellar activity a bit better, maybe. Also, the second thing, so for the strategy, I don't think we can be totally wrong by accumulating 200 hours. It's not like we are really doing like only really ending for very specific moments. But maybe one thing we could do, this is true, is to have a more like a smart scheduling strategy. This was already discussed at some specular conference. So maybe try to do like 100 hours, look for maybe some features, some isolated features. And if we find them, try to have a smarter strategy afterwards, really looking for specific events. But this is a bit more, for me, it would be a bit more influenced. So maybe not the most general case. I don't know really what should be the good strategy here. I'm not sure we can be totally wrong by accumulating so many 200 hours on each target. But there is no new speculators too, so you're kind of right in a way. Huh?
Thank you. Thank you very much. I would like to end by saying I think I really appreciate very much the very positive energy that you brought to the lab in Cambridge. So I think everybody liked you very much. So I really wish you a very successful and postdocs, and I'm sure they will be successful. So,
thank you very much, Didier. I'm looking forward to see you in real life at the next meeting.
Thank you, Elsa. I'm done.
Thank you very much. Now, Brice Olivier de Maury, please, if you have questions.
Yes, hello Elsa, hello everyone. So thank you very much for the very nice presentation. I must say as well that I enjoyed very much reading your manuscript because it reminded me a lot of things that I learned in the past. It's so comprehensive, so detailed that I think this was very nice. I really enjoyed reading it. So thank you very much for all of this. So I got a few questions on the manuscript, on the talk that you presented. That spans a little bit the methods, and that goes to the statistic end and so on. So we just ask these questions at the end. I wanted to start with the stellar contamination. I think this is a really timely issue that will come up as a very important question when we start James Webb observations. And you did a very nice analysis in your thesis when you compare the scatter in and out of transit. And you used the Spitzer data, if I'm not mistaken, to do so. And I wanted to know whether you did the same study using K2 data, because indeed we see in the K2 photometry that we can see this rotation period. Yeah. And therefore the signal that is coming there, can it be witnessed as well in the transit photometry?
So indeed, this is a good point. I didn't do it for K2. So K2, when I worked on the data, it was in 2008, more for this stellar contamination issue at first, but I didn't do what I did for Spitzer. So really looking at precisely at the statistics of the residuals. This is something we should do. I could do totally, and maybe see if I can find any specific. So just to show over there, if I show the two bands. So I think you were mentioning this, the fact that we have a nice variability in K2, not in Spitzer. And no, it's true that I never analyzed really all the raw K2. I really used the transit for this study in 2008. So I cannot really say what I would get.
Do you think that we would have enough photometric precision with K2 actually? Because I saw that in Spitzer, indeed, the level, the scatter is pretty much the same. This is expected because we would see that if, as you explained very nicely, that for cool spots, we would not expect actually something really to pop up in the Spitzer photometry due to the precision, to the fact that these things actually are less prominent, I would say, in infrared. But would you still have at least enough precision with K2 to make actually these spots happen? Or would it need actually to be a huge coverage in spots? Is it still realistic? Is it needed actually? Is it worth going back into it? Or given actually what we got with K2, it's probably not worth it?
I don't remember the exact photometric precision we can have on a single transit on K2. It's like 100 ppm, something like this. Just asking because I don't remember, but I guess
a bit more, yeah.
Yeah, but a bit more. In this case, of course, yeah, it could be tricky, but if you have a big spot crossing, why not? Like, for example, I didn't show it here, but I have I think I deleted it. Oh no. Sorry, I had a, you see in the manuscript, there is this nice spot crossing that we saw in Spitzer, kind of a.
Yes. Mm-hmm.
So for example, for such a, if this is a spot, it's really big in Spitzer already. So maybe the contrast is really big. So in K2, it would be dramatic if we have something like this. So I guess this we could observe, and it's still worth it to look for those kind of big features. But I'm not really sure, like, yeah, maybe we won't get like the tiny ones because we don't have the precision, but still have a good sampling, and it could be worth doing it. Yeah.
Okay, yeah. There are some teasers in your PhD, because indeed this is quite some work in motion. So you did a lot of things, and you have a lot of ideas of new things to do. And in particular, you acquired some data from Speculoos in the I+Z band to try to see whether you could see this variability pattern in I+Z. So now I'm curious. I was wondering, between the time when you wrote up your PhD thesis and now, essentially, you managed to have a look at this data and to see whether actually you see the same kind of periodicity pattern in the I+Z band compared to the
plan. The initial plan was to take care of this in July, but actually I didn't. I got some rest, and so yeah, indeed, you're talking about this, like just adding a new band here and try to do the work that Brett Morris did again, but with 3 different bands. So this is just a snapshot of all the light curve I have in Speculoos, not analyzed, as you can see. That I didn't carry out the joint analysis yet. Looking on it with Lionel, we looked a bit. Seems that there could be some periodic variability. There are some hints that maybe we can identify something, but it's kind of unclear now. I don't want to tease you too much if it's not the case. So I guess I'll come back in a couple of weeks with a real analysis, like a proper one, that can tell you if I can see any periodic variability or not on the I+Z. But it would be nice, like. It would be a good constraint on the photosphere using real data, real observations. I prefer this than using spectral models because it's more coming from observations.
Yeah, of course. No, that would be very interesting. Okay, thank you very much. Now I will finish. I see that the time is passing fast. So we'll finish in the last question regarding the model comparison that you're using. So indeed, we rely very much on statistical tools to see whether it is worth including more parameters in the baseline models, or whether actually for when we do atmospheric theory, whether it is worth adding some methane or removing it, or adding some CO2 and so on.
Yeah.
In your PhD thesis, you use a lot the BIC, the Bayesian Information Criterion, to compare actually, to do some model comparison and to determine actually what is the right, I would say the right set of coefficients that could explain a given AOR of Spitzer and so on in terms of detrending. So the BIC is essentially related to the marginal likelihood, which is the likelihood average over the prior. And this is a bit the question I wanted to ask you. Could it be a concern that actually you are comparing this marginal likelihood? The fact that you've got prior dependent information criteria that you are using. Have you thought a little? I know this is a bit tricky question. There's no.
It's true that I've never really considered it. I kind of used the BIC as like looking at the papers that were published in my fields on the similar topics. I kind of did the same methods. That's true. Just following what was done before, and I never really asked myself these questions. Also, it could be this. There is at some point I found it a bit tricky. Like for example, for the Spitzer analysis, the priors that I used were coming from Leticia's paper that were also derived from the Spitzer paper, from some Spitzer observations, only the earlier ones. And this was quite of a question. Like maybe indeed we are kind of influenced here by the priors. But if I remember well, we asked ourselves this question and we answered. I don't remember the answer we got, but finally, we explained this that it was not a big issue, but I don't remember why. So I remember that I had this in the refer report. I don't remember why, but it's true that I never thought of using another one that is not based on this marginal likelihood, and it could be something to do indeed, and maybe it would change a bit the results.
Okay, I will stop here. Thank you very much, Elsa.
Thank you.
Thank you very much. So Fran Pozuelos, if you have questions, it's the right time.
Yes, hi everyone. Hi Elsa. Thank you very much for this nice presentation. It was clear and easy to follow, so something that I appreciate. In addition, I have to admit that I enjoyed it a lot reading the thesis, which in my opinion is very well written. So first of all, I would like to congratulate you for the work done so far.
Thank you.
And I only have some minor questions. The first one is about your speedster analysis.
Yeah.
At some point, you did some injection and recovery experiments to try to see which planet could be still there. And I would like to know, well, if you could maybe explain a bit more, how did you follow, well, which is the strategy that you follow? When did you inject these synthetic planets in the data? And also, how did you define when a planet was recovered?
Yeah, so sure, I have a slide on it. So that's a cool question. Just my computer is slow, I don't know why. So I will just wait 2 seconds. So yeah, I can talk about it. What I did is to do this injection recovery, I did it on the residuals. And what I did here is to inject, the model that I used to inject it is I use Batman, so to have the model of the transits. I inject different transits. So yeah, this is a graph of the number of transits injected for the different folding periods that I have. And in red, it's when it's not retrieved at 8 sigma. So this is a strong detection, 8 sigma, or when it's retrieved in the blue. So I tried with many different transits, many different periods. And the thing is, what I used to retrieve is a TLS, so transit least square that you know well, the package. So I'm a bit, let's say, I'm a bit, I have to follow the constraint of TLS, which is that you cannot really detect a single event. So every time that I have only one transit in the data, it's not really recovered to high significance. But for the rest, what I use is I wanted to be sure that first I get at the period, or at least an alias of the period, and then that I get good timings, like the timing that correspond to the one I injected. For the injection, I injected them randomly, like never at the same T0. So I vary randomly the T0, and then I vary the period, and I see you're running a TLS, like jointly detrending and running the TLS to see if I can recover the different planets. What I can see here is that pretty much all the planets that when I have two transits, I can go up to a minimal planet radius of 0.4 on spitzer precision, because the precision is really good. So I can detect like a Mars-sized planet if I have a couple of transits in the photometry. But if I have only one, I can't rigorously detect it.
Sorry, this was me. Do you think that there is a real difference in between using TLS and the classical BLS, the box least square method?
So I just followed, like when you read on the package, I show many examples where this is the case, where you gaining from using TLS. It's a more complete model, really using the limb darkening. So I guess I just I used the version of TLS because it was shown in different aspects to be better than BLS, but I didn't discuss why choosing one or the other. I guess with BLS, it would be quite similar results.
Yeah, I think in this case it would be very similar, because actually we have a very red star, and in that case actually we have a box shape, similar to box shape.
Yeah, we are in the infrared, so we are really box shape. That's true.
Exactly. So the efficiency actually of both algorithms are very similar.
Yeah.
I will also ask you about the transit time variations. As far as I understood, you are doing a follow-up with the ground-based observatories that we have, searching for outliers to see maybe if there is maybe a planet that we are still
maybe something
about. I'm curious if maybe you have done the inverse problem. So with all the data that we have now on hand, have you compute which kind of planet actually will be inducing some transit time variation that you can actually see in your data? So
Well,
you can actually rule out already some kind of planet.
I myself didn't do it, but I think it was done in Eric's paper in a part, right, where he made some simulation with an 8 planets. I cannot really talk about it because I didn't carry out such analysis. But indeed, it's kind of the way TRAPPIST-1H was found in, like, we have resonant chain, and looking at the different other possibilities for this resonant chain, looking at what we have in the data. So they say, okay, those different scenarios, they are discarded because we don't observe the transit in the data. There is those remaining scenarios, then they observed and they confirmed TRAPPIST-1H. So kind of the similar scenario that when we found the Neptune using only math. So I guess, yeah, it's definitely something we can do, but I didn't do it myself, so I'm not gonna, I can't really tell you more about it.
Okay, no problem. And the very last question, I promise, is about the target list. Is someone in the consortium actually taking care of update the target list every time that there is a new release of from an stellar catalog, like for example a new Gaia catalog, a new Gaia release of something, including even for example more targets in the target list? There is
so the target list is not supposed to be too much change, but it's not totally fixed, totally freeze in time either. I guess, of course, if we have a new ultra-cool stars that are confirmed within 20 by 40 parsecs and that are really interesting, of course they will make it into the target list. There is nothing is set into stone. But with the nice analysis that Daniel did, like he really like scratched into all the catalogs. So I guess we are pretty much safe for now. But it's true that we have selected all those ultra-cold one, and the limits maybe that we set in spectral type, like for example at M5, maybe we could try at some point decide to extend it to lower type to get a bit more, maybe play with energy with TESS, where TESS is quite efficient. So this is true. Like the target list could be evolving, I guess, and it would be for the best maybe to include more interesting targets.
Mm-hmm. Actually, program 1 and program 2 are highly related with the James Webb and TESS. Do you think that it will make sense to actually build the target list thinking, for example, in the ELT and Plato, which are missions that are coming shortly?
So Plato, I don't think so, because Plato is really going to hint for other kind of stars and more like long periods. But for the ELT, I guess ELT would be great, but I'm not sure we get too much time on it. Maybe for some time, like I guess for the ELT to have some time in the ELT, you must have a planet to ask for some time. If you don't just tell them like observe this star, I'm not sure they will give us time. But yeah, true, ELT should be taken into account as well.
Okay. That's all from my side. Thank you very much, Elsa.
Thank you, Fran.
Thank you very much. So now, Michael, if you have any questions or comments or thoughts about this?
I was like over well the wall, so I don't have any questions. I would like just to congratulate you.
Thank you.
For this very nice work. It was a pleasure.
Yeah, me too.
Wish you the best for the future.
Yeah.
I'm sure the best will come.
Yeah.
Sure, success.
Yeah, we will stay in touch anyway. So Denis, yeah.
I have some time to ask a question.
Yeah.
Okay, maybe I would like to go a little bit outside of your comfort zone.
Oh, atmospheric
Go
planets.
No, it's worse than that.
Oh.
You mentioned that there are some flares, there are some spots at the surface of the star, which indicates that there is some magnetic activity, and associated with that, there's probably relatively strong stellar wind. And since the TRAPPIST are very close to the star, it means that this wind must affect the atmospheres, and it's probably likely that it might wipe out the atmospheres of B, C, D, I don't know for the other ones. So when you are adding up the signal from all the planets, doing that several times,
Yeah.
so
Yeah.
does it make any difference if you're removing one from the group?
That's true that, so I didn't really try all the combinations. What I wanted is to, as much as possible to decrease more the error bars. The more we have, the more we can, because it's decreasing in square root of the number of planets. So in my case, it was not like a general behavior of the inner ones and the outer ones. It was more like trying to get the best signal, and so I would add them all together. But it's true that we can, I think I did it for a comparison of a model. I don't have the plots here, but again, I was quite limited, so I didn't reach any conclusion. But it could be that they have similar behavior more in the inner one that are more exposed to those kind of winds. Maybe the atmosphere are quite different than the other ones. But there are some different scenarios and simulations about the fact that maybe this UV, big UV activity, particularly in the pre-significant phase of the star, it's not necessarily totally, how to say, it's not impossible that an atmosphere has kind of managed to stay and to endure this kind of this difficult phase, and maybe even it can using the photolysis of certain molecule, etc. It can drive some processes. So I think I discussed this in the last part of the introduction, where all this intensified activity, it's not totally a no for habitability, but indeed it's way different than what we could expect for exoplanet in the solar system.
And is there a way to know for sure if there is an atmosphere on B?
I guess the best way I would say is to use MIRI. So next year I will be joining this team MIRI. We're going to look at occultations in 2 different broadbands. And if they detect occultation in the 2 bands, they're going to compare the different depths. And it would be, and the 2 bands are chosen wisely. So they are in the CO2 absorption band. So if there is a strong difference between the 2, because it would be quite precise, we could expect to see the CO2 feature. It would be quite of a direct detection of atmosphere and CO2 in the same time. Of course, if it's not, then the question remains, and we have to continue maybe using transmission this time. As I said, using like a couple of fewer than 10 transits. So I can show you a nice graph actually from this study. Again, the reference again, it is Lustiger 2019. Sorry, I did not say it quickly. You see different types of atmosphere, all the 7 planets, and the number is number of transits you have to accumulate to discriminate between the different types. You can see if you go to CO2, either 10 bar CO2 or 92 bar CO2, only less than 10 transits are needed to see this figure. So if you don't manage to do it in occultation, you might manage to do it in transmission.
Okay, that's a large pressure.
I know. Yeah, it's really large. So the models, like I didn't do the models myself. So yeah, they use, it's quite common to use this 10 bar and 92 bar Venus. One is Venus-like and the other one is like a more, it depends also, like, I think this model doesn't include cloud. Of course you have to include clouds. Clouds could be quite dramatic for us. There are some other simulation on this. You will have to need to get more transit if you want to overcome the clouds, but it's still feasible for the strongest feature.
Okay. I can allow myself one more question.
Yeah.
You showed, there was a question on this about the presence of silicon.
Silicate, yeah.
Silicate, yeah, especially in the core. How important is that for a planet to have silicon in its core?
I'm sure I know the answer. I know for iron, I would say it's because of magnetic to have an iron core to have a magnetic field, but silicates as well. I don't know.
Yeah, actually, you need silicate in addition to iron
to get the core and the magnetic activity.
So this is pretty much important to know if there's still no silicate.
Yeah, exactly. That's why so I kind of like the scenario of a core-free planet, because I find it quite exotic and it's nice to imagine such a thing. But I don't really know how it would work not to have a core if you want to protect your planet from if you have a magnetic field to protect your planet. Maybe it's feasible. Maybe I don't really know.
Yeah, what are you expecting from a magnetic field? What would happen if a planet has a magnetic field or not?
It allows to protect the surface, and protect from the stellar wind and stellar erosion, like we see a bit on Mars, because we have a remnant magnetic field on Mars, but you don't have a strong one, and it's impossible to keep the
Let's
atmosphere.
return to Venus. Venus doesn't have a magnetic field, yet it has a very thick atmosphere.
Yeah,
So
but also, yeah, Venus is almost almost synchrone, like not totally. Yeah, I mean, it's true that those planets as well are going to be as well tightly locked. This is a big question for their magnetic activity too, and they will have also some influence with the tides. So maybe the core, the tides can be strong enough to even influence in this.
yeah,
So
solar tides. Yeah.
I don't really know what to expect for the magnetic field of such a planet, and to really probe this, I don't know what we can use, like because to probe the magnetic field on a long distance, I would say use the aurora. I'm not sure we could detect any auroras on the Trappist planet at all.
Actually, maybe, and you could take advantage of the fact that the star is not emitting in the UV and just a little bit in the visible.
Yeah.
And the auroral emissions will be in
Yeah.
the UV and the visible. So maybe during a transit, you could observe something
Some UV.
because it's happening in the night side
Yeah.
of the planet if it has a magnetic field.
So it could be a way.
And this would be a proof that there is an atmosphere also.
Also, yeah, it would be perfect too. I don't know. I don't at all about the precision needed and what we could expect.
You need photons for sure.
Yeah, you need quite photons.
Okay, thank you very much. I will stop bothering you.
No problem.
So if anybody else has a question, you are very welcome. Or the members of the jury. Oh, maybe I should turn on. No, it was open. So if the members of jury still have a present question, if not, then we can stop here, the defense, and the jury is going to reconvene in another room, and we will return here in about half an hour, so stay tuned.
Perfect. So you can go to, you can stay in the room or, yeah.
No, you don't. Yes, yeah. Okay.
Okay. Awesome.